Uh, yeah, as you know, we're gathered here in a collaborative effort between GSNP and GDS. That's the topical groups on statistical and nonlinear physics and data science on the Nobel Prize. And Jerome and Doug will, in a moment, introduce you to the panelists and tell you about the format. But very briefly, the kLogW seminar is something that GSNP has been running through the beginning of the pandemic. And if you'd like to join our mailing list, please do so. A few timely reminders on behalf of GSNP. The APS abstracts for the APS March and joint March and April meeting is just a week and a bit away, so please get them in. And it's a good time to renew your membership, especially to GSNP. I'll put links in the chat for all of these, but if you're a postdoc or a graduate student who's entering a contributed talk, please consider having your mentor nominate you for one of the speaker awards. Again, I will put the link in the chat. We also run for our junior members of GSNP an annual GSNP t-shirt contest. So please get your entries in for that as well. In general, we're always looking for new people, both from the quantum and the classical world in GSNP, and we welcome your ideas. We're a large group, so let me just quickly go over ground rules. When I'm done, I'll mute you all, and perhaps just the speaker can unmute themselves. Again, we have a number of panelists here and a number of topics to go over various angles on this. If there are questions of clarification during the talks, please put them in the chat, and either Doug or Jerome or I will put them to the speaker at the end. If you can save longer questions for the end of the discussion, so once the panel is done, you're please encouraged to switch on your camera so that the panel can see you. And if you could please post broader questions, comments in the chat box, and again, one of us will pass the questions on to the speaker. So thanks very much. I'll turn it back to Doug to introduce the next couple of speakers, and also Jerome later on to introduce the rest of the panel.
All right. Thank you, Menden. Before we get going, yes, Holly, apparently the number of participants has just hit 300 and other folks can't get in. So I'm hoping that you can increase that limit. I see in the chat you said there is a 1,000 person limit, but apparently we're not going past 300.
I'll take a look at that now. Thank you.
Thank you. Thank you, Holly. So thank you, Menden. Just to emphasize one of Menden's points, that GSNP, please renew your memberships and join if you're not already a member. It'll help us become a division. We're actually on track to do that. And if we can maintain our numbers, we'll become a division. And I think that will allow us to help serve our members even better. So please do that. Thank you to Patrick Charbonneau, who is our GSNP member at large, who has co-organized this event. So Patrick, I see he's online, thank you. And a really big thank you and shout out to Holly Croft from APS, who stopped and turned on a dime to help us put this on and get the word out in very short order. So Holly, thank you very much. All right, so let's turn to the topic. The citation you probably read for the Nobel Prize. It reads, "For foundational discoveries and inventions that enable machine learning with artificial neural networks." So those latter bits sound a little bit CS-y, right? And that resonates with the public. But today we're here to celebrate the foundational discoveries and inventions, the beginning bits of that citation. And these, of course, are all in physics. So we're going to hear about those, and we're going to hear about consequent developments in physics and data science continuing through today. So we're going to begin with two short tutorials on Hopfield networks and Boltzmann machines, and follow that up with perspectives from a panel of experts. And they'll discuss things a little bit after they make some statements, and then finally we'll open it up to general Q&A. So I think this is going to be a lot of fun. Thank you all for joining. All right, so our our first speaker is going to be Yuhai Tu from IBM. And Yuhai, along with one of our other panelists, David Schwab, is a longtime co-organizer of a very popular GSNP March meeting series, many years running now, on statistical physics meets machine learning. Okay, so Yuhai, for his theoretical work spanning many fields, he is a APS fellow through GSNP. He is former chair of DBio. He's winner of the 2020 Onsager Prize, which is jointly sponsored by DCMP and GSNP. So Yuhai has a very, very broad perspective on the physics behind the prize. Yuhai, will you please tell us about John Hopfield and his eponymous networks?
Sure. Can you all hear me or see the slides I put on the?
Yes, looks great.
Okay, good. All right. So I was tasked to do the tutorial on Hopfield fields, so Hopfield model. So what I'm going to tell you is what it is, the Hopfield model, and why is it important for physics and as well as for machine learning. So as Doug said, the citation is a foundational discoveries and inventions that enable machine learning with artificial neural network. And the latter part does sound a little CSC and got a lot of people confused whether this is a prize for physics or a prize for AI. Okay, here I'm going to start my first, before I go into Hopfield model, tell you a little bit about the history of the latter part, the machine learning with artificial neural networks. This is my view, may not be agreeable. I mean, this may not be the universal view of it, but I see it as 3 waves over history. So the first wave came with the invention of neural network in 1943 by McCullough Pitts. I think accredited by that. And pretty soon afterwards, Rosenblatt is using this idea of neural network in the perceptual model to do learning, right? This is a different network. It's a feed-forward network with one hidden layer. And he was able to generate a lot of enthusiasm about AI and what machine learning is, and so on and so forth. The sort of the tail end of this is sort of marked by a book published by Minsky and Peppard, which in 1969 wrote a book, which they proved that one hidden layer perceptual model, the ones that Rosenblatt was building, cannot even learn XOR function, right? So that was sort of the end of the first wave. But the idea never died down, right? So the second wave is the Nobel Prize in physics, what it's about. The key figure in this is Hopfield model, Hopfield, and as well as Geoffrey Hinton in the 80s, and also and it go on to the 90s, where they sort of developed a machine learning model based on neural network, but also based in physics, right? So as such, they were able to not only use the model to learn stuff, to learn things for machine learning, but they were also able to build a foundation for how it works, why it works, where it works. So I think that's probably the reason, I don't know, Nobel Prize was given to physics, physics Nobel Prize was given to these 2 gentlemen. But let's be realistic. The real reason, not the real reason, one main reason is because the revolution, right? So what come after that? So the second wave also died down pretty much until in the early 2010, 2012 is the AlexNet developed by Geoff Hinton, among others, that really started the ongoing deep learning-based AI revolution, which got everybody's attention, right? You have AlexNet, you have AlphaGo, AlphaFold, ChatGPT, and so on and so forth. So these 3, Yoshua Bengio, Geoffrey Hinton, and Yann LeCun got the Turing Award a few years ago, 2018, because it's a new revolution. People feel in all fields, you have to live under a rock without knowing this deep learning-based AI revolution, right? So I think the Nobel Prize in physics celebrating the foundation, but I think the application side is actually very, very important, played a key role in this, made the Nobel Prize in physics really something that is that physics should be doing, is building the foundation for something that can apply have to benefit human society. Okay, without further ado, here is the neural network, Hopfield neural network model. It was first proposed by Hopfield in two papers, 1982, 1984. And the problem it's trying to solve is the associative memory problem. If you want to store a set of patterns or memory patterns of that's characterized by this vector x of j from 1 to p patterns. And then to the purpose of doing that is that you store it and then you present a new pattern y as an initial condition. The network, you want the network to be able to respond by producing one of the stored patterns closest to the new pattern y, right? One of the x1, x2, x3, and 4. So Hopfield developed a model to just do that based on what we call now, a recurrent neural network. Basically, these are network with nodes. These are neurons. These blue dots are neurons. And they're coupled by these, what in physics called coupling constant, Wij. They are bidirectional. So you have Wij and Wji. In the original Hopfield model, Wij is equal to Wji. But nonetheless, because you have this recurrent interaction, it's called recurrent. This belongs to the recurrent neural network, right? In the original Hopfield paper in 1982, he developed the Hopfield model based on the sort of a binary variable, Ising spin, +1, -1. So the idea is that the dynamics of the Ising model in the recurrent neural network is the simple one. It's the one written here, xi at time t +1 is just the sum of all the input at t weighted by the weight w minus bias b, or go over a sign, right? Sign function. So this is nothing but the McCollum-Pitts neural network model, but with a step function activation function, right? So the question is the following: that can you find the weights Wij to achieve associative memory, right? So that's the task. That's the learning task. So the simplest case, I remember the only one pattern is actually pretty illustrative. For example, if you want the state to remember is this vector x with x1, x2, xn as its component, then you say, okay, suppose I give you a different one, and suppose the stability requires that the sign, the actual result of this is bias equals 0, has to be itself, right? So this is a self-consistent equation for determining Wij. And it turns out the solution, you can guess it or you can derive it, is just Wij is simply xi minus xj. Xi, xj are the stored information, that the intended information to be stored. Now, starting with a new state y with the n mistakes, right? It was different from the one you want to recover. You can easily show that the dynamics really did drive you towards the stored x if the number of mistakes, the number of in the original y is less than half of the n, half of the total number of spin, right? That's very easy to show. So the next question is the case of multiple patterns. Suppose you want to pack p patterns. So then you can go to the same type of argument, the stability requirement, and so on and so forth. So I don't want to get too much into the details, but you can see that you want to require this so-called interference term to be bigger than 1 for the state to be, if it's bigger than 1, it becomes unstable. That means interference becomes too strong. You cannot distinguish two stored patterns. Right? Okay. So there goes what. So many results come after the proposal of the Hopfield model, including one. This is a very striking result, which is saying, okay, can you actually compute the capacity of the network given n spin or n neurons? What is the maximum number of patterns you actually can remember? And here, a landmark result by Amit et al., Amit, Gutfeld, and Samplinsky, published in 1985. In a physics journal, PRL, that was shown that it's actually the capacity is linear with a coefficient like this. The reason I say that is that actually the Hopfield neural network, as people mentioned here, was not the forefront of the new AI revolution, but they are recent development trying to use the Hopfield model or a modified Hopfield, including Hopfield himself, who published a series of papers trying to push this towards dense associative memory or modern Hopfield model. This is work done with my colleague here. He's a former postdoc, Dima Krotov, published in a series of papers and others that actually push the limit of going beyond the linear limit, right? If you change your activation function, then you're actually capable of storing more patterns within a network of n neurons. Okay, all right. I think the nice thing about the Hopfield model is that it lends itself to all kinds of physics tools and concepts, in particular, the energy functional that exists in the Hopfield model, for us to understand it as a physicist, right? For us to use the tools and ideas in physics to tackle this problem of learning. For example, in the symmetric case, Wij equals Wgi, it's not hard to see this energy functional. In other words, the Hopfield model, it's easy to show that the memory states actually sit at the minimum, energy minimum of this energy functional in this high dimensional space. Actually, indeed, the many machine learning problem can be mapped into an optimization problem in the high dimensional space. All right, now, so the most, of course, the Hopfield solved the problem by using a social memory problem by using this ANN, and the application is actually demonstrated by the Nobel website. It's a very nice picture. So the information or the stored pattern are the energy minimum in this very high energy landscape. If you start your state here somewhere away, by iteration or dynamics, you actually can recover the right pattern, right? So here, there's a couple of movies. You can see that if you start with partial image here, and you recover the full image after several iteration in a neural network that's being encoded, that stored this full image, right? And also from Dima, you have another picture of this very nice picture. If you start with partial information all over the place, but very random in the beginning, and if the network actually stored this image, you actually can recover it based on this initial distorted picture. Okay, all right. Let me go forward. As I promised, so why is Hopfield model important? There are many things people can say, and I think a lot of people in the panel can contribute to this discussion. But to me, at least, there's two things that I think it's very much worth mentioning. One is Hopfield model provides a physics-based model, right? Spin glass model in this case, for associative memory, a learning task. And in this case, computing is carried out by dynamics of the underlying physical system. So using dynamics of some physical system to do computing is something quite interesting, quite new, quite important. And second is that Hopfield model really exemplifies a very deep connection between machine learning and physics. That is, the learning is really can be considered as an inverse physics problem. Therefore, physics can be very useful. For example, in the Hopfield model case, physics is the spin glass physics. Basically, knowing the interaction Wij between the spins, we try to understand the collective emergent behavior of the network dynamics, right? But the machine learning is turned the other way around. You say, well, how I want a certain behavior to come out of this model. How do I design the weights, learn the weights, so that the desired state are reached? In some sense, this is really the inverse physics problem, machine learning. All right. So final slides, where we go from here, right? Are we done? Are we done with building the foundation and making discovery for the machine learning? No, the answer is absolutely not. Much remains to be done. There are at least two directions. I mean, physics for AI, this is what we're talking about today. I think currently the deep learning, there's really a lacking of theoretical foundation for the current deep learning architecture and its algorithm. It's still missing. So building a theoretical foundation for deep learning as spin glass theory is for Hopfield model is really, really important. And it's the job of physicists, I think. Also, there's another side of the story, which is, AI is so powerful, but yet it's still very challenging to learn simple physical law from data, right? Developing new interpretable AI tools for scientific discovery is really, really important. And I think if we understand how the current deep learning network is working, we probably have a better chance to develop better tools, AI-based tools for scientific discovery. Along these two directions, let me do a little bit of advertisement. Herbert Levine and I have co-edited a special features collection in PNNS a few months ago, published. So I encourage you to read about that, about various pieces in that collection that address these two directions, physics for AI and AI for physics. Finally, I think as Doug mentioned, David Schwab and I has been organizing the invited session and focus session on statistical physics meet machine learning for the last few years since the pandemic. So please submit your work to the sessions and join us in this endeavor. Thank you.
Yes. Mm-hmm.
Doug, you're muted.
Thank you. I forgot. Thank you, Sara. I forgot that Menon muted us all. Thank you, Yuhai. That was really nice. Next, we're going to turn to our second presentation by Pankaj Mehta from Boston University. There, he works at the broad and growing interface at the intersection of theoretical physics, theoretical biology, and machine learning. So, along with our panelist, David Schwab, we've been hearing about a lot, Pankaj wrote a wonderful article entitled A High Bias, Low Variance Introduction to Machine Learning for Physicists. So as both a researcher and an educator, Pankaj is really super well positioned to tell us about Geoffrey Hinton and his Boltzmann machines. Pankaj, the floor is yours.
Thank you so much for organizing this. What happened to my keynotes? Shoot. As usual, I messed up Zoom. It was time to do stuff. Let's try to do it this way. This is probably a bad way of doing this. Sorry. Can you see this or no? Oh boy.
Yeah.
Hello?
Yeah.
It's okay?
I see it.
It's great.
It worked. Yeah.
Oh, okay. So let me start. I'm going to tell you about Boltzmann machines, which I think to most physicists are much, much less familiar than Hopfield models, even statistical physics. So as you can see, the Nobel Prize citation cited Geoffrey Hinton, especially for these new networks called Boltzmann machines. These can learn to recognize characteristic elements in a given type of data. Hinton used tools from statistical physics, the science of systems, and built from many similar components. So I think, I heard from many people that they weren't sure why this was a physics prize. So I think what I hope to do is over the next 10 minutes, convince you, tell you what is a Boltzmann machine and what is its relation to statistical physics. And as Doug mentioned, we wrote a review like 5 years ago, because we thought it was important for physicists to learn these techniques. And chapter 15 and 16 are actually dedicated to what these Boltzmann machines and other what I call energy-based models. So as Yuhai was alluding to, one of the things that's really interesting is in traditional statistical physics, we usually start with some known function or probability distribution. Here, of course, we have the famous Boltzmann distribution. And our goal is often to calculate observables, some predictions of the model, or maybe even if we're ambitious and more numerical, to draw samples. And this is usually done with Monte Carlo methods. And the energy function and the parameters and the couplings that define the energy functions are learned from physical arguments, scaling, symmetries, things like that. So I think what is going on here is much more in the line of what I would call inverse statistical physics, and especially inverse statistical physics using energy-based models. So the basic idea is that I want to learn some probability distribution. And I'm going to assume that the way I want to learn it, the probability distribution I want to learn, can be written in a Boltzmann form. So e to the, this partition function times e to the minus beta times some energy function. And the goal is to learn couplings and parameters of EX directly from data or observables. So this kind of inverse statistical physics idea has a long history in statistical physics. I think the first real formulation of thinking about statistical physics in this way, in my opinion, were these seminal papers by Jaynes, where he basically invented these maximum entropy methods. And the idea there was to take the data, right, in this case, observed values of some observables, and from that directly construct the energy function. And the parameters here, of course, are these Lagrange multipliers, which are the generalized thermodynamic forces we all know so well. So after that, I would say another example would be what Yuhai was saying about Hopfield, where the data is the attractors to be stored as minima. And the idea is then I learn the couplings and construct the couplings explicitly, as Yuhai said, by basically taking the outer product of these memories. So the Boltzmann machine actually solves a much, I would say, in some sense, a much harder problem, where instead of observables or some memories that I want to store, what I instead have is data. So I have examples from the data distribution I want to learn. And the question is, can I make a Boltzmann-like distribution that actually just takes examples and learns the parameters of the energy functions? And so the basic idea of this is what Hinton and Terry Sejnowski basically called the restricted Boltzmann machine. And the idea was that in addition to the visible variables, the x's that I can see directly, for example, in these handwritten digits, the value of the pixels, each pixel, I'm going to introduce some extra hidden variables. These hidden variables are often called latent variables. And what I'm going to say is that I'm going to basically posit that there's a joint distribution between these visible variables, x, which I can directly observe, and some hidden variables that I can't directly observe, but I'm going to still assume things have this Boltzmann form. And the idea is that I'm going to then posit a very specific form for the energy function. And the specific form that was posited was that each visible and hidden variable had a local field associated with it, but the only couplings that were present were between hidden and visible units. So there's no direct couplings between visible units or direct couplings between hidden units. And instead, there are just couplings between visible and hidden units. And I'll try to give you some intuition for why you would want to do this in the next slide. So the basic idea is now I give you data and I want to learn back these AIs, WI alphas, and these B alphas. So why would I want to introduce hidden variables, and how do I learn this procedure? So again, the idea, as I said, is a very brilliant one. It's something that should be familiar to many condensed matter physicists and most physicists. The idea is that what I'm going to do with what these hidden and latent variables do is something like an inverse Hubbard-Stratanovich transformation, for those of you that are familiar with Hubbard-Stratanovich. The idea is that what I'm going to say is actually all the correlations between visible units, all the correlations that I can see, are actually induced by these hidden variables. And in this way, you can do compression, or basically, in some sense, say that there's some underlying physics underneath all this stuff that is basically giving rise to these things. So it's like an inverse Hubbard-Stratanovich. And so this seems at first glance at a very restrictive kind of thing you can do, but it turns out to be quite general. So again, the idea is that I introduce these hidden variables. All the correlations are induced by these hidden variables. And basically what happens is that if I integrate out over these hidden variables, if I marginalize over these hidden variables, I can represent very complicated probability distributions over just the visible units. So how do I learn these couplings? Well, the couplings are learned by maximum likelihood estimation using gradient descent. So the idea is I just choose the couplings that maximize the probability of the data. And in order to do that, I could just do gradient descent, where I keep updating the parameters by taking the derivative with respect this log likelihood with respect to the parameter. So that at first glance, that seems like a very hard thing to do, but it turns out precisely because I've chosen this very specific form of the coupling where only visible and hidden are coupled to each other, but there's no couplings between the visible and the hidden, you can basically calculate these gradients very explicitly, and they turn out to be something very intuitive. They turn out to be the correlations between hidden and visible variables as calculated by my model, minus the same correlation calculated directly from data. And because I can calculate this, I can actually calculate these correlations both by just basically calculating the things from data is very easy because I have examples. So I can just use my samples to calculate this directly, the thing from the data. The thing that's harder to calculate the things from the model, but basically what's happened is some kind of Monte Carlo scheme, usually alternate Gibbs sampling is used and some approximate version of it in order to calculate this correlation. So once I can calculate the correlation functions, I can calculate the gradient, I can maximize these, and in this way, I train my model. So here is some example. My student, Tiago basically did this. So here are two, famous, commonly used data sets about 10 years ago, not anymore, 15 years ago. One is MNIST, which is, the examples that you train your machine on are handwritten digits. The bottom shows you, as you're training, you get better generating these. The bottom is something called fashion MNIST, which is just, black and grayscale images of things. And you can see that, you'll see something that says epoch. That's basically how long I've been training it. You see that the training gets better as I do these things. And again, it's kind of interesting because basically you've said there's these hidden variables that induce all the correlations, yet this kind of structure allows things to be learned quite well. So let me say, as was suggested, one of the things that's really interesting is, of course, that once I've learned a probability distribution, right, I can generate new examples from that probability distribution. And this is what's called the generative model. And this has become, as 5 years ago, this was very hard to explain. Now everyone understands what these things are because everyone's played with diffusion models and ChatGPT and generate new things. But the basic idea underlying it is just a statistical physics thing. Once I learn a probability distribution, it's easy to generate new examples by appropriately sampling from it. And so what the RBM suggested, and I think it was very unclear at the time, is that we can learn and sample from much more complicated distributions than the ones we usually consider in physics, which are translationally invariant, usually have lots of symmetries, some kind of sense of scale. And the same kind of statistical physics techniques, but in reverse, in the inverse form, can be used to do these things. So one of the things that I'd like to say is that there's often this sense that these energy-based models are not useful for anything, but often when you have limited amount of data, or in certain, especially scientific settings, it's turned out the RBMs have been used quite successfully, I would say. So here's an example from Martin White and Rama Raghunathan's group, where they basically used RBMs to basically sample protein sequences of an enzyme that needs to be functional. They learn a statistical model to generate novel new sequences. And some of these sequences give rise to proteins that have very high enzymatic activity, but never occurred in nature. Another thing, my former postdoc, Charles Fisher, has a company that has gotten a lot of money, where what they do is they use these RBMs to basically make digital twins for medical records to try to basically predict how people's disease progression is going to go. And part of the reason they use RBMs is because you have very limited amount of data, because they're working with historical clinical trial data, of which there is very little. So many of the classical traditional generative models, which are very data hungry, don't work. Another setting for RBMs has been to exploit this idea that correlations between visible things are easiest to represent using some hidden units. And this RBM kind of ansatz has been used as a variational ansatz for quantum wave functions quite successfully. There's a nice review in Nature by Roger Melko and others that discusses these things. And so despite what you might hear, I think RBMs are still being used, especially in scientific settings and in settings where you don't have access to infinite amount of data, which is kind of given when you're training on text and images. So I guess that was basically my overview of RBMs. And I'd like to second what Yuhai said. I think there's a huge, rich set of problems at the intersection of machine learning and statistical physics, both in applying statistical physics to really understand what's going on, because I would argue no one really understands what's going on in these models, even though we can measure every parameter and know exactly how they're trained. And on the other way, of course, there's a rich thing, as you saw from these variational RBMs, for using these machine learning techniques to try to understand physical systems better. So that's it.
All right. Thank you so much. That was great. So there have been a number of questions coming in through the chat, but thank you for those. I think we'll wait on the questions until after we hear the perspectives from the panel. So Jerome, would you like to unmute and take over?
All right. Well, thank you, Doug. So I think, well, I'll say a few words since I'm GS chair, and I guess, I would miss my duties if I wasn't going to do that. So I think it's wonderful that we were able to come together to have these two enlightening talks from Yuhai and Pankaj, and move to the next phase of our, let's say, afternoon with the panel and some experts discussing machine learning. So just a quick few words about GDS. So we are the group of a topical group on data science, so GDS. We encourage you to join us. I mean, obviously, we are also very close to the becoming a division, and we have some sessions at the March meeting, so the global summit. Sorry. So I encourage you to check them out and submit if you'd like to do so. So without further ado, so as I mentioned, I mean, it's wonderful to come together with GSNP and GDS to have this great series of talks, and the success, I guess, is shown by the fact that we reached the ceiling. So an unfortunate consequence, but we'll hopefully everyone will be able to see the recording. So now let's start with the second phase of the afternoon. So quick rules of the game. So we're going to have a panel with 4 experts who are going to give their perspective on machine learning and physics on these Nobel Prizes. So we've asked the panelists to give maybe a first 5-minute perspective. Then we'll give time for the panelists to give some follow-up on these questions, and then obviously we'll invite back Yuhai and Pankaj, and we'll invite all panelists to answer questions from the audience, which will be our opportunity to interact with all of you. All right, so I think we're ready to start for this second part, so with the panel session. So we are going to start with Sara Solla from Northwestern University. So Sara, if you are ready to unmute and tell us about your perspective. Thank you.
Doug, would you
Thank
mind unpinning Pankaj and pinning Sarah, or making me co-host?
Say that again.
Sorry, that was a request for Doug.
Everything works, Sarah. I mean, if you're ready, feel free to
Yes, I am. Thank you. So thanks a lot for the invitation to be part of this. So I want to start by telling you about my own experience of John Hopfield. So I was a postdoc at Cornell University, and I had done my PhD thesis on renormalization group and phase transitions on XY models of Gaussian Lithauris transitions in the presence of disorder. And at Cornell, I was, I was Neil Ashcroft's postdoc. So I was collaborating with him in a study of metal insulator transitions using percolation, and I was collaborating with a geophysicist doing earthquake models also using percolation. And I went to a meeting of the American Physical Society, a March meeting in 1993. And I had assigned on my schedule, all the many short talks that I wanted to attend. And suddenly I had a gap, and I decided to go to a plenary talk, because the plenary talks are always a little bit more didactic, more pedagogical for people who are not in the field. So I walked into this room where John Hopfield was giving a talk about his 1982 paper. And of course, I had studied spin glasses. David Sherrington is here today. I had studied the Sherrington-Kirkpatrick model. I knew all the math that he was using, but he was using this math in the context of talking about storing memories and retrieving memories. And this for me was totally amazing. The whole idea that one could use a physics model that was initially designed for studying magnets and look at the dynamics of this model, again, following physics rules, following Glauber type dynamics, to understand how the state of the system evolved in time, and use these ideas, the idea of the system where the landscape, the energy landscape, has multiple minima, and that each minima has a given basing of attraction. Use this idea to store memories and retrieve memories. So the whole idea that such a system could process information was totally amazing to me from a physics. I never thought of a dynamical system as a system that processes information before Hoffield's ideas. And the other incredible idea was that in physics is this reverse problem that we alluded to in the previous 2 presentations. that is the idea that in physics, we try to understand what are the interactions. The interactions are there in nature. We try to investigate them. We analyze the forces. We describe the forces. And given the forces, given these interactions, we try to understand what is the behavior of the system. The learning problem is the inverse problem. We have a desired behavior in the system, and we have to infer the interactions that would allow us to achieve this behavior. So these are the two great ideas, I think, behind the Hopfield work and the Nobel Prize given to it, which is the idea that a dynamical system, that the dynamics in a physical system is actually a tool for processing information, and the idea that the interactions can be tailored for the system to achieve a given goal. And then the specific brilliant idea in the Hopfield model was the idea of computing with attractors. You know, the fixed point attractors in the system that were for him a way of storing and retrieving memories have been extended, and are very, very powerful ideas in neuroscience have been extended to the idea of line attractors that are relevant to, for instance, managing the position of the eye in the horizontal plane and stabilizing it to look in a given direction. They have been used to understand the encoding of head position as an angle type variable. And more recently, we have adopted this very powerful idea of computing with manifolds, understanding that a very high-dimensional neural system is such that its dynamics is confined to low-dimensional manifolds, and these low-dimensional manifolds are attractors in the very high-dimensional space of the neural state, which is, you know, millions, if not billions of neurons. So the whole idea of computing with attractors is a very, very powerful idea and has had an important, a crucial influence in neuroscience. I think Nicolas Brunel will expand on that later. And in this context, I wanted to remember our colleague Daniela Mead, who unfortunately passed some years ago, because Danny was a very strong, I think he reacted to Hopfield like I reacted to Hopfield. You know, he just fell in love with the idea and was a very strong proponent of exploring this notion of computing with attractors. Actually, he's the one he was a nucleation point for the Jerusalem group and all the Amit Gudfredson-Polinsky papers that studied the Hopfield model very carefully from a statistical physics point of view. And then he actually wrote a book that was called Modeling Brain Function, The World of Attractor Neural Networks, where he explored all the implications of attractor neural networks for neural systems. Neural systems, I mean, composed of real neurons, and from the point of view of behavior and cognitive abilities of networks of real neurons. So I think if Danny had been alive, he would have been part of this Nobel Prize. I would have loved to see him there being recognized for his work. And just to say that Hopfield was really extremely influential in this idea of using dynamics to process information and emphasizing the importance of tailoring the interactions. So to close my presentation, I want to tell you that when I came back from that March meeting, we had a Cornell tradition in the group of Neil Ashcroft that we will spend the first couple of weeks at the group meetings telling each other what we had learned at the March meeting that was exciting. So when it was my turn, of course, I went to the board and I talked about Hopfield. I talked about the Hopfield model and Hopfield's ideas. And, you know, I took a few minutes to explain all that. And then at the end of my presentation, I remember Neil Ashcroft, who was a very, very well-established solid-state physicist. You know, he was the author of the famous Ashcroft and Mervyn book on solid-state physics. He tilted his head in his usual sort of very faint way of expressing disapproval. And he told me, Sara, that is very interesting, but it is not physics, is it? And, you know, this week when I have heard all these really nasty comments about why the Nobel Prize was given to two computer scientists working on AI, comments coming from my colleagues in the physics community, I remember Neil Ashcroft's idea of saying, It's not physics, is it? And I thought to myself at that point, I was not, old enough to answer back, but I answered back to myself, and I thought to myself, it might not be physics, but this is the kind of work I want to do. So I don't know if you would like me to say something else, but that's my 2 cents about Hopfield networks and Hopfield's work.
Thank you very much, Sarah. I think there will be time for follow-up comments, but let's see the perspective from all of our panelists, and we'll come back to you and the others after this initial round of discussion. All right, thank you again. So our next panelist is David Schwab from the Graduate Center at the City University of New York.
All right, can you hear me?
Yes, we can.
Okay. Great. So I want to spend my few minutes thinking about the future of the physics of AI, and to make the case that these big models that we have now, they should really be considered as serious objects of scientific study, no different than the brain of an organism that evolved in its environment, or a material that we find has interesting properties. I think it was said before that these are systems where we can measure every degree of freedom that's involved. We can ablate in any way that we want, and we still don't understand how they work. Just because we created them doesn't mean we understand how they work. We expose them to an environment, if you will, and they have sort of incredible emergent behaviors that go far beyond theory. So I mainly wanted to make that case and sort of mention a couple of different areas where if this isn't something that you think about, things that you might want to read up on and learn about some of the interesting sort of emergent properties of big models these days, where I think physicists could play a role. And so the first one that comes to mind is something called in-context learning, where in these big language models, they're trained on some big data set, but you can ask them something that is outside of the scope of what they've ever seen before, teach them something new. They don't change their parameters, but they can change their behavior. And how this emerges, what are the principles behind that? What are the learning dynamics? What are the mechanisms by which that's implemented? Are all sort of really interesting questions that are really physics questions, fundamentally. Even more basic is questions of why do models generalize? I think the approach that has come from sort of worst case analysis has left our understanding of why you can train a model on some data and it'll perform well on other data. The sort of empirics have left our theory in the dust, and I think a physics-based approach is the way to go from here, both for regular generalization from samples to new samples, to out of distribution generalization on samples with a shift, and even to generalization across different tasks. And then the final place where I think there's more that physicists can do that I would mention is the origin of these language model scaling laws. So the past 5 years has seen these models get bigger and bigger and bigger, trained on more data, more parameters, more compute, and the way that people had confidence in being willing to spend $100 million, $1 billion, whatever, to train these models was that they saw very predictable scaling laws in performance, and those seem to be borne out. But we really don't understand fundamentally where they come from, and this is a place for physics. So all in all, there's a lot of really interesting and fascinating emergent behavior of these big models, where I think physicists can play a big role in the future. Thanks.
Thank you very much, David. So again, there will be time for follow-up comments in the next section of the discussion. So our next speaker is Eun-Ah Kim from Cornell University.
Hi, I'm Eun-Ah Kim, professor of physics at Cornell. I am a quantum many-body theorist interested in understanding experimentally observed phenomena from solid-state systems and simulators of solid-state systems, and interested in questions inspired by experiments. Over the past 8 years, I have been exploring the use of AI algorithms to delve deeper into the complexities of quantum many-body physics as they manifest in experimental and simulated data. So I come more from the angle of AI for physics, but with or without AI, I approach questions triggered or inspired by experiments through minimal models, the models that are minimalistic, that attempt to capture the essence of what might be most important. And this requires a judgment call on what is essential without knowing the ground truth, because we often cannot solve the model. The microscopic models, which tries to keep every single details, and hence we turn to minimalistic models. And the model of interest might turn out to be too minimalistic for some things, but nevertheless, often such pursuits lead to new understanding. So from this perspective of someone who has not been looking at neural networks as sort of a system of interest by itself and relatively new to this, I think this year's Nobel Prize celebrates, nevertheless, the quintessential example of impactful physics. It celebrates how physicists who follow their desire to minimally model interesting phenomena from fundamental interest can end up benefiting humanity, even when that wasn't what necessarily they were trying to do beyond they could have imagined, possibly. So in my research, I'm currently exploring using different type of recurring neural network from the Hopfield network. What I'm exploring is called recurring neural network, RNN. The Hopfield network, as Sara described wonderfully, offers, and also Yuhai, associative memory system. RNNs are also recurring neural network, but they are more flexible and better suited for processing sequences of data, such as language. So I am leveraging RNNs and other language model architectures to capture time correlation in many-body quantum dynamics in quantum simulators. Quantum mechanics is a theory of dynamics, and with quantum simulators, we have unprecedented control and ability to study quantum dynamics. But studying this time correlation requires new approaches and new tools, and ability to access new axis, the time axis, which wasn't something that we needed to study if we are studying equilibrium physics. So we are finding purposefully designed minimalistic machine learning models can tell the distance between quantum many-body states that are spanning exponentially large Hilbert space, even when order parameter is unknown. I also use generative probabilistic modeling, as in the Boltzmann machine, to uncover underlying correlations and trends in large and complex experimental data. These efforts enabled discoveries from large volumes of X-ray diffraction data, including the revelation of signatures of Bragg glass. As Pankaj mentioned, my community is also actively pursuing expressive machine learning architectures as the framework for variational many-body wave functions, another use of generative modeling. And these neural quantum states outperform previously known variational wave functions for some problems. But as David mentioned, because we don't understand how these generated models and their expressive abilities scale, or where it is coming from, there is some limit. There is quite a bit of limits on understanding when, how these neural quantum states will work the best. So I think there is a lot of room for exchange and synergy between these two directions to benefit both sides. In closing, I just want to share that for me, starting to venture into the world of AI and learning sort of the past origin of how it started, but seeing where it is today has been a really exciting adventure, especially because having these broadly useful tools break down barriers. It allows me to communicate and collaborate with people that I wouldn't have known how to talk to and collaborate with. When you can share the same tool, when you identify same data-centric problem, it allows us to communicate across the barriers and find mutual interest and open new doors and lead to unexpected synergies. And it's been all just very exciting. And I'm really excited about this year's Nobel Prize, and I echo what everybody else have been saying. This is definitely a physics prize. It exemplifies the power of physics.
Thank you, Eun-Ah. So now we're going to give, I guess, the floor to our fourth panelist. So Nicolas Brunel from Duke University.
Okay, well, first, thanks to the organizers for putting together this webinar. This is really a great idea. Yeah, I think this is really amazing news for statistical physics. In fact, this is the second time in 3 years that the Nobel Committee has recognized the huge impact that statistical physics has had on really different fields that are outside traditional physics after the Nobel Prize of Giorgio Parisi in 2021. So then I'd like to come back to some of the points that Sara has already made. So Sara mentioned also the impact of Hopfield on neuroscience. And in fact, it was quite surprising to me when I read the report of the Nobel Committee that it was exclusively focusing on AI and machine learning, but did not mention at all the impact that Hopfield has had on neuroscience, which to me has been perhaps as important or maybe even more important than the impact on machine learning and AI. And I think, so Sara mentioned that how she basically discovered this model through attending a talk by John Hopfield. And I think that's the experience of many statistical physicists or physicists of that time that got attracted to questions in neuroscience just thanks to that paper, that 82 paper. Both Yuhai and Sara have already mentioned, the Jerusalem trio, Danny Amit, Hanor Gutfreund, and Chaim Sompolinsky, that successfully solved the Hopfield model analytically using tools from statistical physics. But there are many others. And importantly, I mean, these people, they didn't stop after they saw the Hopfield model. They actually went on and explored many other models and questions in neuroscience. And in fact, so these physicists participated in the creation of a new subfield of neuroscience, which is called either computational neuroscience or theoretical neuroscience, depending on who you ask, that is now really considered an integral component of neuroscience. And in fact, at the time of Hopfield, neuroscience was basically a purely experimental field. There were no theorists in neuroscience department. But now, 4 decades later, physics have really percolated very deeply in this field. And in fact, one good indication of this is that the last Brain Prize, so the Brain Prize is arguably the most prestigious prize in neuroscience. So the last Brain Prize earlier this year has been attributed to 3 physicists, right? So Larry Abbott, Chaim Sompolinsky, and Terry Sejnowski. So I think it's a testament to the impact that physics have had on the field of neuroscience. And also, so just wanted to come back a little bit also to other issues that Sara has already brought. So in fact, the main conceptual impact of the Hopfield model on neuroscience is this idea of computing by using dynamics, so convergence of neural systems to attractors. And also so the idea that you have a simple model that embodies crucial ideas about how neuroscientists think about memory storage and memory retrieval, that you store memories through modifications of synaptic connectivity in specific neural circuits, and then that you can retrieve these memories by using the dynamics of the network. And at the time of Hopfield, of course, this was like purely theoretical. And in fact, many neuroscientists were highly skeptical about these ideas. But more recently, progress in experimental techniques have allowed people to test these ideas directly. So now we are able to perturb the activity of neural circuits using fancy new techniques, particular technique called optogenetics, where you can activate neurons with light. And people have been able to test these ideas using these methods and actually show that, in particular in flies and mice, that the results of these experiments are entirely consistent with the idea of attractor dynamics. So I think this is a really very exciting time to be working in this field that's, you know, at the intersection of physics and neuroscience. And Hopfield was really a major one of the big pioneers of this field. Like, this is really the reason why many people started to go in this direction.
Thank you very much, Nicolas, for your perspective. So before we actually open the floor for questions, maybe, you know, if our panelists have, you know, some follow-up comments, some follow-up things that that they weren't able to cover during the first 5 minutes. I mean, if there's something that you'd like to add first, feel free to do so. Any volunteer? Okay, so if not, then I'm going to start inviting back Yuhai and Pankaj and share some of the questions that we've received. So I'll start, you know, with the last one. So Pankaj, question for you. So I guess the question is how one draw a sample corresponding to one. So a question from Kim in the chat.
Yeah, so generally the way in these more primitive generative models, that's been one of the big advances in the last 4 years, which is like how...
Okay, would you mind just repeating the question?
Oh yeah, so the question was,
It's
there were a
good
bunch of technical questions about RBMs that I tried to answer in the chat to spare everyone. But the newest one was that I have this RBM that learns, say, all 10 digits at the same time. How do I sample a 1 if I want a particular 1 instead of a 0 or a 9 or something like that? So I would say one of the big advances in an RBM, it's quite difficult. What's usually done is that if you look at the latent space and say do a PCA or some kind of dimensional reduction, you'll see that different digits usually corresponds to different sections of that latent space. So you try to sample from some particular initial hidden unit to try and hope you get a 1. And if you don't get a 1, that would be similar to the hallucination question that was asked before. More recently, one of the big progresses in the last 4 or 5 years has been another very physics-based idea, which is like contrastive learning, where the idea is now you basically have labels, right? Say I have a label 1, 2, 3, 4, 5, 6, 7, 8, 9, and I try to basically, and then I have this hidden vector space, this latent vector space. And what I try to do, and so instead of labels, let's say you have text and I want to generate some images, what you do is you jointly embed the text and the images to the same latent vector space, so that text, and by this joint vector embedding using a minimization of another energy function, this is usually called contrastive learning, you can generate conditionally. So again, the whole idea is, again, you're going to always sample and you're going to try to make conditional distributions, and you're going to try to embed stuff in latent spaces such that vectors that correspond to the same concept in different modalities overlap strongly, and things that correspond to different concepts don't overlap as much. I guess that would be my technical answer to this thing. I hope that is good enough to answer that
Thank
question.
you very much, Pankaj. So the next question is maybe for you, Yuhai. So a question from John Haller: is the inverse physics problem similar to a dual solution model, like how you can convolve 2 functions by transforming into dual Fourier space and multiplying, and more broadly, solve machine learning problems by solving physics problems?
I think there's some, I mean, I don't know for sure that can be worked out. But that's the actual direction. One of the direction we are pursuing to try to understand it is that, so if you think about machine learning, it's by changing the weight, right? But the effect is that the neuron activity space. But it turns out there's some simple duality between the changes in the activity, which is what people usually call the neuron activity X, and the W, right? So if you change something in the W, which is by learning, is equivalent to change something in the X space. So there's some duality relation. It does exist in certain cases. I think that's sort of, in my way of thinking about it, it is really the inverse problem in some very sort of a representation of the inverse problem can be think about as changes in the X space versus changing in the weight space, how they map to each other, right? So if you understand that within certain setup, I think that's a way to think about how this inverse problem, I mean, it's just a picture, right? Being one problem being the inverse of the other problem. What are you going to do with it, right? So if you figure out a mapping between what I call duality between the weight space and the activity space, then you have a way of using this general concept to actually understand how, for example, in our case, we actually did discover one of the duality between, weight change and the activity change. And we were able to use that idea and that particular duality to tackle the problem of generalization, for example. What makes the solution more generalizable is in the weight space. If you look at the loss landscape in the weight space, is all those minimum that have a broader attraction basing or have basically flatter. And that corresponds to something that in the X space, in the activity space, being more tolerable to changes in the activity space or in the input space or the output space. So I think this idea is general, but how do you use it really depends on whether you can find this mapping between the real world observable X and the learned activity, the weight, which is sort of hidden in some sense. Not in the sense that Pankaj is telling you, but in my way of thinking about it, X is what you usually measure. Weight is not something you measure, you tune it, right? So you want to get some behavior in the X by changing the weight, by learning the weight. And if you figure out a way to map these two one to another, that actually can become a very powerful way to going forward. That's just my 2 cents. We're still, figuring this out, but I think this general idea of this may be some duality between the two worlds, the machine learning world and physical world, may be a helpful one.
Thank you very much, Yuhai. So I see that Sara has raised her hand, so I'm going to give you the floor, Sara. So one thing that I wanted also to ask you, Sara, is you raised a comment about Heb and his contribution. So if you'd like also to say a few words about that.
Yeah, because it's related. I just wanted to comment on the previous comments. The question, as I said before, in physics, we know the JIJs, we know the WIJs, and we try to do statistical mechanics in the space, which is the safe space of the variables in the system. And the question of learning posed a very interesting problem, which is to do statistical mechanics in the space of interactions. And this was the very pioneering, beautiful work of Elizabeth Garner and Bernard Derrida, who actually studied the partition function in the space of interactions for fixed data and tried to understand the capacity and try to understand how you exclude some configurations of the WIJs and keep others. So that gave rise to a very interesting class of problems also in statistical physics. The question that this is a question that in some sense Hopfield avoided because he decided to choose the WIJs to be of the Hebbian form. And Yuhai mentioned that, and I think that Pankaj mentioned that also. In the Heb idea is that neurons that fire together wire together. So if you have neurons that are very correlated in their activity, you should put a WIJ between them. You should write down an interaction between them. It's because they interact directly. And the way Hopfield chose the WIJs for his model was in this Hebbian spirit. And therefore, he avoided the question of learning the WIJs. He used the memories to create the WIJs, which is the simplest way, in some sense, of solving the learning problem. It ignores questions of sequences, for instance, that were brought up later, because it ignores the temporal effects. It's neurons are fired together, but it doesn't say that neuron A made neuron B fired a few milliseconds later. So it avoids this temporal detail. So it's a very simplistic way of describing the interactions, but it's a way to get started, which is what John Hopfield did.
Thank you, Sarah. So another question for one of the panelists. So all right, so I'll let you choose who is going to answer that one. So it's a question from Inge Petersen. May randomization group theory be used for machine learning? So who would like to take that question?
Pankaj. And David.
Maybe.
David, would you like, oh, Pankaj, sorry, go ahead.
David, go ahead.
David.
No, please. You've thought about this one recently.
We hope.
Let me just say why I point to these two guys. They are the first to actually propose to use it and actually did something, which was not very successful in, I gather, but it got a lot of citation because a lot of interest. So there's my.
Yeah, I think part of it is that the kind of systems that are being studied here are certainly strong disorder RG is what we need. And me and David did some other version where you had very local couplings and something with the Ising model. At least in some toy cases, it has something to say. But for the kind of real systems, I would say, certainly if we're going to use RG, it's going to be some version of strong disorder RG or something to do with disorder RG, but it's very unclear what the scale invariance is. We don't know what the scaling theory is to begin with. So RG usually comes from a scaling theory. I don't know. Maybe David has something to say.
Not about that, but yeah, that old approach that we had was working on a connection to some techniques that people had in machine learning and neural networks that at the time were very important, but sort of fell by the wayside once we had better ways to train feed-forward models. And so I think that's the main reason why that connection ended up being less useful than it could have been. That said, that people have been questioning whether Hinton, should have a physics Nobel Prize. When we were arguing that paper was that, what he has implicitly discovered by doing this was RG from a very different perspective, for what it's worth.
Maybe I can add something to this mix. I think that, as David mentioned, that there are future direction to consider in terms of building a physics foundation for machine learning, and for example, in particular for large language model. There are these scaling laws, which really reminded us of the scaling law we see in critical phenomena. Basically, what it is that if you keep having but what they plot is the loss versus the compute. What is compute? Compute is the number of parameter times the iteration, right? That's how many iteration you go through, or data, right? In that case, you don't even go to one. I mean, the data times the parameter is the compute, and then you see a very clear dependence. I mean, to call it a power law may be too much, but the scaling, the dependence continues down as you keep increasing. If you do it right, in terms of number of compute and number of data, so it reminds, a lot of aspects of it reminds us of some scaling law we see in critical phenomena. So it's very, tempting to us to imagine that there might be a scaling law dependent on some kind of RG, because you can say you can scale up the data and scale up the compute in some proportionality or some other scaling dependence, and your result in terms of the training loss or test loss will just go down, right? And or the training system is near some critical point that this would happen. Or, there are a lot of questions need to be answered, of course, along the way, but I think that's a very fruitful direction to consider, as David was suggesting, in the future for statistical physics, right? So that's sort of the scaling law, right?
Yeah, I agree, but it is worth keeping in mind that with most of those scaling laws, at least the earlier ones, you increase the size of your model and you increase the number of tokens or amount of data that you train on, and you do it in a proportional way. So the proportion isn't 1-to-1, it's 1 to something, but it's a constant, which means that in some sense, we're more towards like a memorization regime, right? If a new token comes in, there's a new parameter to learn it. And it's a little bit unclear to me the extent to which these are scaling laws of learning versus scaling laws of memorization.
Yeah,
but I think it's interesting, this Krotov work with Hopfield that was mentioned earlier, I think by Pankaj, I believe, that there are extensions of the Hopfield model that are what are called dense Hopfield networks that allow for capacities that are not linear. So the parameter is not just P over N. It's not that P scales like N, but P can be exponential with N, and which is very interesting. And the other thing that is very promising, I believe, is in this new Hopfield version of Hopfield models, is their connection to transformers. And whether this will give us a handle to understand from a more conceptual and theoretical point of view why transformers work as well as they do, for instance, in large language models, in LLMs.
Thank you. Another question. So for Nicolas, so question for Patrick Charbonneau. You mentioned that neuroscience did not initially welcome ideas from physics. What helped change their perspective? What did it take for that to change? So Nicolas first, and maybe Sarah will have to add something after that. But
yeah, well, I think it's a great question. Well, I think initially the two people from the two fields spoke completely different languages. And so it was basically hard to communicate, right? Because I think the neuroscientists didn't see the value of highly simplified toy models, because they were thinking more of models as being very detailed models that describe all the details of their experiments. And so they thought that, abstract models of the type of John Hopfield were of no value because they were, in their view, too far from their experiments and from the reality of the real brains. And I think what changed is that years of communicating together. Also, I mean, the physicists did a lot of work in actually working on much more realistic models and showing that actually for instance, the main features of the Hopfield model are essentially unchanged if you implement these ideas in much more realistic models. In fact, again to mention Danny Amit, that was one of the big, I think, results that he obtained, is to show that you can actually go much closer to the experimental reality, and actually all the main ideas of the Hopfield model are still present. And so progressively, I think there was this realization that from neuroscientists that actually theory can be helpful, and that when models started to make testable predictions that they could test in experiments, and then also on the side of theorists to learn more neuroscience to be able to talk to experimentalists. So I think there was kind of convergence from both directions.
Sarah, would you like to add, because Patrick also mentioned your name as a possible person to answer the question? So yeah. Oh, yeah.
Sorry, could you say the question again?
No, I said you were also mentioned as one of the experts to answer a question from Patrick. So the question is about neuroscience and what made
it's a very interesting question. When I joined the faculty at Northwestern, it was in '97, so it's almost 30 years ago. My faculty line is in the Department of Neuroscience. I have a secondary appointment in the Department of Physics. But my colleagues in the Department of Neuroscience had never seen a faculty member who didn't have a lab. So the whole idea that my group was a theoretical group, that we did mathematics and then we did simulations and we ran programs. So the whole notion of a theoretical neuroscientist was a bit incomprehensible to them. It's really kind of a mystery to me how they hired me. But for me, it was fantastic to be immersed in a neuroscience environment because it allowed me to do what Nicolas was talking about, which is to develop the vocabulary, to start looking at real data, to start modeling real data, to the point where my work was useful to them. You know, it allowed them to gain insights. For them, models was a box, another box, and an arrow that connects these two, say this influences that. But quantitative models were not really the rule, except for people who were working at a more cellular level and knew the pioneering work of Hodgkin Huxley, let's say, who had equations for the creation and the generation of an action potential. But people at the systems level, which is what I have concentrated on, which is networks of neurons working together, didn't have the notion of conceptual frameworks or quantitative work. And it's to me very, very heartwarming that 25-something years later, I look at the ads for looking for postdocs and looking for faculty, and so many people are looking for faculty in computational theoretical neuroscience. So it's really a cultural shift, and it's taken 20-something years, and the mechanisms behind it are the ones that Nicolas pointed out, that we as physicists becoming more knowledgeable about neuroscience and using the appropriate vocabulary and the appropriate terminology, becoming aware of what the important problems in neuroscience, and the neuroscientists learning the value of modeling that is quantitative and that unveils mechanisms, as opposed to modeling that fits the data. You know, one can do beautiful models that fit the data, but if the models don't allow you to unveil a mechanism, then this model is just maybe a useful tool for simulations, but it's not really helping you gain any understanding of what is driving the system. So it's been a fascinating cultural shift. And for me personally, in my career, I said it started with John Hopfield. It started with an interest in neural networks. I worked at Bell Labs with in the same group as Jan LeCun and Joshua Bengio for 11 years. But then I became really interested in how the brain works, in neural networks as a model for the brain. And it's been a wonderful opportunity to learn about such an interesting system. And I think as Laurette put somewhere in the chat, what is physics? Physics is what a physicist does, because I can see my work, and my work is I am a physicist thinking about neuroscience. I'm not a neuroscientist. I'm not trained as a neuroscientist, and I don't know as much as a neuroscientist do, but I'm not limited by the neuroscience conceptual approach to how the brain works.
Right, thank you. I have a question from, I'm going to relay some general questions to the whole panel. So from Doug. So the topic of what is physics has been raised. Most of us would probably agree that physics involves interplay between theory and experimental observation. Can you name some good examples of this for the behavior of Hopfield networks and Boltzmann machines specifically? So for the entire panel. Who would like to? Nicolas, if you'd like. You unmuted yourself.
I mean, I could expand a little bit on what I said about the Hopfield model, or this idea of computations by a tractor being tested experimentally in recent experiments. So the basic idea of the Hopfield model, let's say you have only two memories in your circuit. So if you perturb the state of the network a little bit, if you're in one of the memories, it shouldn't change this very much. So basically the network should come back to the unperturbed state, right? But if you perturb it very strongly, potentially you'll go to the other attractor, right? So it's basically And this was actually tested in, for instance, there were experiments in mice where mice have to basically have two possible. So basically, it's not really memories. It's like this decision-making experiments. So yeah, they have two possible decisions they have to make, but then there is a period before they actually do the decision, which is basically this period where the experiments are consistent with the system going in one out of two attractor states. And they've done these experiments where they basically they apply these perturbations in various ways, in multiple ways, and it's exactly consistent with what you would expect from a Hopfield type model. So that's just one example, but one simple example. But there have been other experiments. For instance, Sara mentioned these line attractors. There was these beautiful experiments in flies where people can perturb the activity of specific structures in the fly brain, and again, this is really consistent with having attractor states. So that's another example.
Thank you. And another question, I guess, about efficiency of computing. So essentially, Jane Wang asked if there's hope to reduce the cost of computing using large-scale neural networks, and do you see ways by which physicists could contribute to making more efficient algorithms?
I can take part of this one. Certainly, I think it's a big question right now, how to make these models smaller and more efficient while preserving their functionality as much as possible. There's a lot of research going on, whether it's quantizing parameters, pruning individual weights in a structured way, perhaps skipping layers entirely, and just going to the end. People are definitely looking at ways to reduce the energetic costs of running these things. At a very high level, this is a question also of sort of model reduction. You have a model that has a huge number of parameters and it does something. You would like to reduce the number of parameters while preserving the function in the ways that matter. Going back to the RG question, there's a bit of a flavor that sounds sort of similar. I don't know if there's any actual meaningful connection there, but there's a flavor.
Thank you, David. So I guess we are close to the end in terms of time. So Doug and
can I add a comment?
Of course, yes. By all means, Yuhai.
Previous question, not this one, not the current efficiency. That's a very important question. But the Doug's question, right? So I don't know the example for Boltzmann machine, and I'm not the best one to give those examples of theory and experiment. But I know one thing. I think Pankaj raised his hand about example in those cases. But I know one thing, that's not the case for the current deep learning arena, where experiment totally outspace theory. So this should serve as a call for theory. Okay, so it's not physics in that for deep learning, not yet, because there's no sort of meaningful exchange between theoretical understanding and experiment, quote unquote, right? So this should serve as a rallying cry for physicists to actually get into try to understand it from using the physics tools and concepts or whatever. So that's my 2 cents. Okay, sorry.
Thank you, Yuhai, for your comments. Doug, Menon?
Maybe I can add an RBM.
Of course, Pankaj, go ahead.
So for example, this example I showed you about proteins, where the people trained RBM, they basically took a bunch of measurements on enzymes across the kingdom of life. They measured how effective it was, and they used an RBM to generate new proteins, right, using this RBM, and they showed that it had very high enzymatic activity. And this sounds trivial because you live in the age of AlphaFold and alpha all that, but actually null measurements almost don't exist at all. So you're always in the small data limit. And this is the best example I know of that. And the other thing I'd say, adding to Yuhai, is to me, this understanding the statistical physics of these kind of matter with function. This is a term Hopfield liked to use always. matter, or still uses matter with function, is I think the frontier of statistical physics. And to me, this strikes me as very similar to early thermodynamics, the numerical experiments, as Yuhai was saying. We have all these empirical phenomena. As physicists, we suspect there's some universal truths behind them. You know, people are building more and more elaborate steam engines, but we don't have thermodynamics, and we definitely don't have statistical mechanics. And to me, this seems like an opportunity for statistical physicists to run wild. So I would say the whole field is numerical experiments, but experiments nonetheless, the same way that engines were experiments that gave us StatMech, right? So that's the analogy I make in my classes. I think it's really actually 100% accurate, though you could dispute with it. And that kind of answers why I think this is physics. Someone asked that again. I think it's most certainly is statistical physics. I think it's very hard to argue it is not statistical physics. So now if you want to say statistical physics is not real physics because it's about emergent phenomenon, what I would say is it's really the end of it's not reductionist physics, which has dominated the 20th century. This is more about emergence in statistical physics. So I think I wanted to give my little, sorry, the comment got me a little riled up. So I wanted to defend statistical physics as a worthy enterprise. And I tell you that, like, sometimes I feel like I'm not a physicist, and the moment I go and talk to a biologist or a machine learner, I realize I'm 100% a physicist. That's the easiest way to learn you are by going to talk to non-physicists.
I couldn't agree more. You warm my heart. I completely agree with you.
All right, thank you. So next question is for Eun-Ah. So what's the future, or what future applications are machine learning going to enable in, let's say, quantum medieval system and perhaps quantum computing?
Ooh. So Pankaj just mentioned matter or system with function, right? So in quantum many-body physics, we talk about materials with functions or materials with targeted properties. And figuring out how to go after materials with targeted properties is an extremely difficult problem. Ab initio can get us only so far. And I think we are now entering a very new era where we have accumulated data, that the database curation have been the effort of previous decade through materials genome, etc. And now we have all this data. We don't yet know how to learn something meaningful out of the data that we are rich in. So figuring out how to make use of the data we have, and at least exhausting what can we learn from them. Maybe extreme properties such as high TC superconductors are sort of an outlier, which is really hard to get out of machine learning. But we haven't yet exhausted the data that we have. Sort of a principled way. So principled approach to the data will the curated database of materials towards prediction will be very exciting. Another exciting direction is, as I mentioned, the Hilbert space of many qubit system is exponentially large, which is supposedly the promise of quantum computing, but it also makes it challenging to figure out what the heck is going on in the system that you have in hand. And in order to make value, get something valuable out of these systems, it is very obvious that we need to approach it from quantum classical synergy. And machine learning can be very helpful in taking the systems that we have and getting us to the next level of generating value out of them.
Thank you, Eun-Ah. So I guess we have perhaps time for one last question. So to Yuhai, a question from Majid Das. So what is the fundamental problem? So again, an open question. So what's the fundamental problem in building the foundation of deep learning and this very new model from statistical physics worth exploring and having potential to solve this problem?
It's a great question. We're still searching for the answer. I think what David actually alluded to earlier are for me, okay, this is just very biased personally. I think the learning dynamics, how do we learn? I mean, we talk about the greatness of Hopfield model is that turning dynamics into a learning, a computing paradigm, right? Dynamics of underlying system. In Hopfield's case, it's a physical system. In this case, you may argue this may not be a physical system in terms of this is all feed-forward neural network, that the connections are not bidirectional, therefore there's no trivial energy landscape, and so on and so forth. But nonetheless, it's dynamics. I mean, after update, you figure out the solution by updating your weights, right? How do you learn? That's what I call learning dynamics. How does learning dynamics work in this huge, high-dimensional space? What governs the dynamics? So we have made some progress in that direction, but it's far from being done, right? I mean, there's just a lot of open question. And next question is, again, very personal, is what makes the solution? Because in this very high-dimensional space, it's very easy to find a solution. But the problem is going around is that there are too many solutions. Which solution is better, right? So this goes to the question of generalization. How do you decide which solution is better? And if you know about that, then you can design a better algorithm to actually reach the more generalizable solution instead of reaching some local, not local minimum, and not so generalizable solution, right? So these are the two key questions. I think these are pretty general. So this question you can ask for any type of different neural network. Like we have done a lot of work in feed-forward, multi-layer perception type model. You can ask the same question for this large language model or the transformer-based model. Well, I think the jury is still out, on these two questions. There are many, many other questions like the scaling thing we talked about by David. This is a very curious behavior. So if you really want to find out, we actually written that, PNNS collection or introduction for that, just for the purpose of identify some of the questions. And we have a lot of experts that contribute to that special collection about some. They already have some thoughts about how do you figure out what the key questions are and how do you might be able to approach it. So I really invite you to actually look at that special issue, which, it had a lot of thoughts that we put a lot of thoughts, and many authors have put a lot of thoughts into that, considering what are the interesting question in both directions, from AI to using AI to solve physical sciences problem, including protein folding. Okay, that was the one good example, very good example we said that, but also physics for AI. How do we build a foundation and what are the question we need to answer, right? Anyway, so that's a very long answer to your question, is that we don't know, but we have some idea what might be the interesting question to go after.
Thank you, Yuhai. So maybe
to that, one of the things
Sara,
that we have learned from playing with artificial neural networks is that we don't have to worry about the curse of dimensionality. If you take a recurrent neural network and you wire it at random, its dynamics which take place in an n-dimensional space where n is a number of neurons. If you take a recurrent neural network and you train it to perform a given task, we find that the dynamics occurs in a low-dimensional manifold. And therefore, the study of the dynamics and the finding of appropriate solutions and the finding of solutions that generalize better doesn't have to occur in the n-dimensional system. We look at neural data of thousands of neurons and find manifolds that have dimension 10, 20. It's not just the brain, it's the real world. If you look at a data set like ImageNet, which is so popular for training deep learning machines, these images live in a 150,000 dimensional space. The data set consists of 14 million images that can be classified in 20,000 categories. But then when you look at where these points are in this 150,000 dimensional space, where are these 14 million points? They live in a manifold of dimension less than 50. So the brain has evolved to deal with a world in which not all possible sounds are sounds, not all possible combinations of pixels are images. It's a world with very strong correlations. These correlations force the data to live in a manifold, and therefore what we have to learn is the manifold. We don't have to learn the full space of data. We have only to learn the manifold in which the data lives. So all these ideas that we're exploring very high dimensional spaces, and it's like looking for a needle in a haystack, finding the solution. I think my experience in working with artificial neural networks had demonstrated to me that this is an incorrect idea, that the distribution of data in the real world and the dynamics of trained networks trained on that data, create low dimensional manifolds, and we only have to look for solutions and study the dynamics in these low dimensional manifolds, which makes our work possible. So we are not looking in 150,000 dimensions, we are looking in 50 dimensions when we want to classify these 14 million images. And that's actually very, very important.
Thank you, Sarah. So I think we've had, or we could go on with questions. So I see in the chat that some questions are getting answered as we talk about with let's say many of the questions branching into other fields, like for instance the one on the chemical master equation. So I think in the interest of time we are going to close this session. Do get if you'd like to join me in concluding and in thanking first our speakers, experts, our unit members who came with us to discuss this topic, and this great news that the Nobel Prize were awarded to Hinton and Hopfield. So
yes, indeed. Yeah. So it's very exciting for our community, and it's gratifying, and I thank all the panelists very much for quickly responding and eagerly participating in this event. I think it was very illuminating, and I feel inspired. So thank you very much. All right. Thanks, everyone.
Thank you, everybody.